Okay, now we're on 1.5, which is atomic structure and electron configuration. So we'll go through this quickly. Most of it's review from your first year of chemistry. The learning objective is to represent the electron configuration of an element or ions using the Aufbau principle. The Aufbau principle, it's German for from the bottom, basically. So you start down here and you go up. Atoms composed of negatively charged electrons and positively charged nucleus that is made of protons and neutrons. So you have to know these words in any elements box on the periodic table. There's the symbol. There's the atomic number, which is usually up there. That's how many protons it has. Sorry, that should be a 6, not a 12 for carbon. For carbon, it's a 6. And then the mass is the protons plus the neutrons. But if this number is not a whole number, then it's an average mass. It works for individual isotopes, but if you look at all of the atoms in the universe of that element, it's not going to be a whole number, because if you average two whole numbers, usually you're going to get a number that has a decimal in it. And electrons equal protons in neutral atoms. So if carbon does not have any charges, if it's not positive or negative anything, it's going to have 6 protons and 6 neutrons. Just know that. Okay, then we have this table to fill out. So if you want to follow along, we'll do a few of these. If you don't need to do any of this, great. Then don't. Okay, so lead, I find it on the periodic table, and it has an 82 above it. So that number goes there. It's the same as the protons. So this one, these two columns are always going to be the same. The neutrons that this lead has, we actually don't have enough information here. So we would need to know the mass in order to find the neutrons, because you take the mass and you subtract the protons. But just for whatever's sake, I am going to find lead on the periodic table and round it. So if I just round what's on the periodic table, it has a mass of 207. So I take 207 minus 82. Oh man, is that 125? I really hope that's 125. I should probably be using a calculator. And then since this is neutral, there's no charge, the protons equal the electrons, 82. Okay, this next one has an atomic number of 34. So I find 34 on the periodic table, and that is selenium, Se. Has a mass of 79. 79 minus 34, I think I can do that one in my head, is 45. That's how many neutrons it has. And then again, the electrons are going to be the same as the atomic number or the protons, because there's no charge. This top one I am now just realizing has a charge. I'm used to seeing the charge over here, so that's why I didn't catch it right away. But this is saying that it has a charge of positive 2, so I need 2 more protons than electrons. But I'm not allowed to change the protons. You can't change this. First of all, it's written there, so you can't change it. Second of all, you can never change the protons. If you change the protons, it's a different element. So I can change the electrons, though. Electrons are on the outside of atoms, and they're really easy to add more or take some away. So I just took 2 away, so that I have 2 more positive thingies, so that it's 2 positive. Okay, let's do another one with a charge. So let's hop down to phosphorus here. That's negative 3. So phosphorus has an atomic number of 15. I have 15 protons. I can't change that. That has to be 15, even though there's a charge here. It's not giving me a mass, so I'll look that up on the periodic table. If I round it, it's 31. I'll just pretend that's what it is. So that means it has 16 neutrons. 15 plus 16 is 31. And the electrons, I need to have 3 more negative particles. Electrons are negative. So 15 plus 3 is 18. And we're going to move on, because if you want, you can do that for practice. Come see me for answers. Or I'm sure you can look them up on the internet. Okay, Coulomb's law is used to calculate the force between 2 charged particles. You're not going to be doing that. So this is a relationship equation. It's not on your formula sheet. You don't ever need to do calculations with it. But you need to understand it. So this equation is the exact same as Newton's law of universal gravitation from either 9th grade or whatever physics you've taken. What that basically says is the bigger the planet and the closer together they are, the stronger gravity will be. So if you're a super huge planet, it's going to have strong gravity. If you're really close to that planet, it's going to have strong gravity. If it's a small planet, it's going to have no gravity, or little or smaller gravity. And if they're super far away from each other, it's not going to have much gravity. You know, there's galaxies that are ridiculously massive, but they're so far away from us, they don't actually affect Earth's gravity. Atoms are the same. It's the same formula. Q1 times Q2 divided by r squared. M1 times M2 divided by r squared. So the r squared is the same. That's the distance. So this is saying that the farther the electron is from the nucleus, the weaker the force of attraction. The closer the electron is to the nucleus, the stronger the force of attraction. The Q's here stand for charge. So if I have a nucleus with 8 protons, that'll be a positive 8Q. And then if it's just between the nucleus and 1 electron, the Q2 will just be negative 1. So then if I have positive 8 nucleus is oxygen, I believe. So then if I go down a row and I have a sulfur atom, sulfur has a nucleus of positive 16. So if we look at 1 electron's interaction with oxygen's nucleus versus sulfur's nucleus, there's going to be a stronger force of attraction between sulfur and its electrons than oxygen and its electrons, if they're in the same place. Remember the rings around the atom? So here we have to be comparing apples to apples. So let's say these electrons are on the first ring. So the electrons on the first ring in oxygen and sulfur, the ones in sulfur are going to experience about twice the force because it has twice the charge. In atoms and ions, the electrons can be thought of as being shells, so those are the rings, and subshells, which are sublevels, which are kind of like areas in the rings. It's described by the electron configuration. Inner electrons are called core electrons, outer electrons are called valence electrons. The electron configuration is explained by quantum mechanics as delineated in the Aufbau principle and exemplified in the periodic table of the elements. So what this is basically saying is electron configurations are a thing. You have to know the difference between the core electrons and the valence electrons, and that the periodic table is actually arranged based on electron configurations. Very exciting. There are some exceptions to the rules that you learned. You don't need to know the exceptions at all, I don't think. Okay, so this is the order that you have to follow, the arrows. So I do this arrow first, then this arrow, then this arrow, then this arrow, then this arrow, then this arrow. So it does not just go from 1, 2, 3, 4, 5, 6, 7. It has to go in this weird zigzaggy order. You also need to know that S electrons can hold 2, p orbitals can hold 6, d orbitals can hold 10, and f orbitals can hold 14 electrons. So that's how many electrons you put in each space. What else do you need to know? I think that's it. So gold has an atomic number of 79, which means it has 79 electrons. So you have to start at the lowest energy level, which is number 1. Sometimes you'll see this inverted so that you're starting from the bottom when you do this, because it's Aufbau, it's from the bottom. They try to do that sometimes. Anyway, we have to basically fill all these up until we get to 79. So the way that we write it is you start with 1s, and then the superscript looks like it's squared. This is how many electrons are in there. So I have 2 electrons in the s orbital because now it's full. All of the orbitals need to be completely full except for the last one. The last one is the only one allowed to not be full. So until we get close to 79, we don't have to worry about that. We're just going to fill them up. So after 1s is 2s, because that's the next arrow. And then after 2s, we go to this arrow, which doesn't start here. It starts over here. So I start at 2p. Fill that up. I'm only at 10 electrons. 2 plus 2 plus 6 is 10, not even close to 79. So then I go to 3s, 2, I'm at 12. Then I go to 3p, 6, I'm at 18. Then I go to 4s, 2, I'm at 20. Then I go to 3d, 10, I'm at 30. 4p, 6, I'm at 36. 5s2, that's 38. 4d, 10, that's 48. 5p, 6, that's 54. Getting there. 6s2 is 56. 4f14 is 6070, so we're getting really close. And then I believe it's 5d9. Will get us to 79. So there it is. That is the electron configuration for gold. So this is my inside-most electron. The core electrons, all of these are core electrons except for the outermost s and p. So we have to find the biggest number on here, the biggest big number. We got 1s, 2s, 3s, 4s, and 5s, and there's a 6 here too. So our biggest number between those is 6. So it's the biggest numbers s and p. So of my 6 big number, it's just those. So this has 2 valence electrons, and then 77 core electrons. Okay, the noble gas abbreviation. This we do the same thing, but we pick a noble gas. So the periodic table has the electron configuration in it. There's a very poorly drawn periodic table. This is the S block. This is the D block. P. Oh yeah, down here's F. There they are. So what we need to do is find the noble gas that completes the P block. So over here, these are all the noble gases. Helium down to, what is it? Oganescent, I think. I don't know if it's on your periodic table or not. Anyway, these are all noble gases. You have to pick a noble gas that is closest to the number we're trying to get to, but does not go over. So the number we're trying to get to is 79, if we're doing gold again. So xenon is 54 here. And then radon right below it is 86. So gold is in between xenon and radon in number. So you pick xenon. Let's do blue again. So xenon picks up my first 54 electrons because this is element number 54. So instead of starting at 1s and going all the way to 5d9, I can start wherever xenon leaves off. So if I find xenon on my periodic table here, and I go all the way over here, what row down is it? 5th? So it's 1, 2, 3, 4, 5, if you're looking at your own periodic table. It's the noble gas in the 5th row. This means that 5p is full. Xenon's 5p orbital is full. So that's where I leave off. So 5p is done, so my next part is 6s. So now I do 6s2. Remember, this was 54, so now we're at 56. Then I do 4f14, we're at 70, and then 5d9. So it's much shorter. What this does is it takes all of the core electrons and puts them in here. And these can be thought of as the valence electrons. Really, only the 6s2 are the true valence electrons, but metals are super weird, and they do a lot of super weird stuff. So sometimes these F and D can act as valence electrons, but that's not going to be on the AP test. But that's why they're left out here, because they can be involved in bonding. Usually it's only the valence that are involved in bonding, but sometimes the F and D orbitals will bond in certain situations. If you need more help with electron configuration, come see me, because this is review, so you got to be kind of good at it. The relative energy required to remove an electron from different subshells of an atom or ion from the same subshell in different atoms or ions, ionization energy, we're going to do that later this unit, so don't freak out about that, can be estimated through a qualitative application of Coulomb's law. So that's the gravity analogy that I did. Basically, the closer an electron is to the nucleus, the harder it is to remove that. Or if the nucleus is more positive, like sulfur is more positive than oxygen, it'll be harder to remove it from sulfur. This energy is related to the distance from the nucleus and the effective shield charge of the nucleus. Valence electrons are easier to remove than core. They're farther away from the nucleus. Transition metals place d electrons last, but they are not valence, technically. But sometimes they can bond. This is why when transition metals ionize, they lose their s electrons first. So the d electrons are technically core electrons. So if we are losing the easiest electrons to lose, they're going to be on the outside, which are the s electrons. So the s electrons will be removed first. So if we take gold, and I believe gold has a charge of +1 is its most common charge. It can be +3 as well. What's going to happen is gold is going to lose one of its s electrons. So let's start with what we had with it uncharged. We had xenon, I believe, correct? And then 6s2, 4, oops, I almost wrote 5. 4f14, and then 5d9. This is the neutral gold. If I want to make it gold +1, I need to lose one electron, and I lose an s electron, not a d electron. Leave everything else alone, remove the s if you have d electrons. So then this one would just be xenon again, if we're saving time. 6s1, 4f14, 5d9. And that's that. I think we're done. Great job.